Thank you so much for your kind invitation. So let me start by, thanking the organizers, particularly Jyoti, for following very meticulously with me. So, Dr. Lakshma Reddy, the chief guest, my good friend Dr. Rakshavir Jatra of Reliance, Professor Khandal, Sri Vilas Taude, Sri Rajiv Ranjan, Sri S.K. Pandey, and Dr. Rakesh Kumar Vij, and other invited guests. What I'm going to talk about on the theme is the opportunities for practice of green chemistry and engineering in oil and gas sector. To start with, since some of you actually, Dr. V mentioned about the importance of chemistry and chemical engineering. So, and I'm going to ask you this simple question. Can you show any three man-made materials, equipment, accessories, or products in any place which are made without use of chemicals? So just look around where you're sitting right now, whatever chair you are sitting on or standing or playing with your computer or mobile phone, all those things included. Or a beautiful house like this, maybe because of Corona, you're staying somewhere far away. And so there is a price of 100 million pounds waiting for anybody since 2008. And this question is still lingering. Nobody can show anything without chemicals. So chemical industry is the most essential and critical industry, which even my friend Dr. Jasra also pointed out. So what is the COVID effect? The energy scenario across the globe has become topsy-turvy. And this happened some time back. The price war between Saudi Arabia and Russia had already brought down the prices substantially during the past few months before Corona, and the Corona effect further affected the spot price. And nobody had even heard before negative price for crude oil in that happened in April 2020, and newspapers started putting things, how it is going to affect and what recession will be and what not. And definitely it happened, and slowly it recovered to another low. So the Brent crude oil spot price averaged about $18 per barrel in April, and it is now about 42. And unless the oil price rises to about $45 per barrel, the industry will not be viable, as some of the pundits are predicting, and that is right. So what is happened in the United States, the effect on fracking particularly, the fracking business is affected to the level of extinction, and 7 of the most active such companies in Texas have already cut down $7.6 billion from their budgets as a response to this ridiculous oil price. And the Energy Information Agency of the United States predictions are somewhat hazy. And of course, we know now the restrictions on travel have been lifted, and obviously, this new norm which we are facing right now will continue until such time when a vaccine of therapeutic is available across the world, and almost 50% of the people are vaccinated. Even otherwise, lockdown will be lifted with new ways of lifestyle and movement. So EIA has further predicted that the Brent crude oil price will increase to 32 barrels during the second half and $48 on average, reaching to something like $54 per barrel by the end of 2021, which is based on the expected worldwide consumption of about 97.4 million barrels per day, okay, during the second half of this year. So in this connection, I want to show you this particular slide. And this is, this particular slide is very interesting because you see that we have about 410 ppm of CO2 in the atmosphere. And if there is no technological intervention, whether you talk about carbon negative, carbon neutral economy, you can see that if we do not have that and our energy expectation grow day by day, we will have carbon dioxide something like 2000 ppm by the year 2250. that means we will be sinked, sank rather in water like Mumbai city. So what do we do? And so this what it means is that although we have signed the Paris Agreement and we say that the temperature should not rise beyond 1.5 degrees C during this century, you see that if when the 20 to 50, if it rises about something like 7 degrees C, you can see it will be catastrophe. So so-called pralay or mahapralay. Okay, so, in order to do this, let us understand what energy sources we are using. Because this is ours is a carbon-based economy. So we know this oil and natural gas. So unless we find some new sources of oil and natural gas and also recovery methods, the BP projection says by 2054 we will not be left with any oil at the rate at which we are consuming it. So when we have gas to liquid processes, crude oil to chemicals, like Reliance has also announced that. So you can imagine, so future refineries will have a variable, production depending on demand. Some part will go to fuel, some will go to chemical, and even in some refinery it is almost 45%. So so we also have this coal business, coal to gas and coal to liquid. And on the other hand, where a lot of people are talking about this renewable carbon or biomass, whether you use chemical conversion, biochemical or thermochemical, and we have big program in ICT, and I was champion of many of these things. Very recently, during this COVID period, we wrote a very important paper. Okay, and this is just today it has come on the on the web portal. So this is the whether whatever carbon you use, ultimately the end is CO2. And I showed you previous two slides. That means CO2 has to be tackled. In future, we may have some sort of a CO2 refinery, that is CO2 conversion into chemicals and that. And this is what we have been doing in ICT. And I must acknowledge ONGC, who have been supporting my research since 2006 in this particular area. And this is related to hydrogen production from water, hydrogen water splitting. And we also have another project where energy storage, where we can store solar energy. So we are taking water, and also there's so-called biogas, which have CO2 and methane. So we can see that we have a cycle here from which we produce hydrocarbons. I have a patent on this. Now we can produce methanol, DME. We have just signed an agreement with one of the companies where they will produce DME, and DME will be a substitute to LPG. Your formic acid, which goes in fuel cells, formats. Incidentally, ONGC requires many of these potassium and sodium formats. Syngas, then you can go to Fischer-Tropsch synthesis, alcohols, or ammonia, fuel cells, hydrogen vehicles, electricity, you name it. That means this is, if hydrogen is there, which is a carbon negative economy, and I've been professing this for a long time now, that I think India should go for hydrogen economy right away and did not wait for the crude oil to exhaust. So since it is a oil-based economy, we wrote this paper, and this will, I'm sure about it, it will generate a lot of heat in the industries. Many of you can read it. It will be available next week. You can download it freely, because we have deliberately made it open access because of many reasons. And there are many interesting ideas in this particular paper. And I'm sure the bureaucrats read this, what we should do, particularly with reference to fuels and chemicals. And we have analyzed, including how carbon is valorized, and the end result of that is carbon should not be burnt as a fuel. Carbon should be used to make chemicals. So, for example, in ICT, we had this 2G ethanol technology. While it is good, government is giving subsidy and you can use it, but the cost of 100 rupees. In fact, what it means that you put in money to make that ethanol as an environmental protection method. So instead of burning ethanol, why not make ethylene and other things, for instance? And if you are going for solar energy, the renewable energy, whether it is tidal, wind, whatever, in future there will be a mix, or including the nuclear energy. So we have discussed this in this paper, how to bring sustainability, and how to use biomass, whether it is used thrown away biomass by farmers or waste biomass or anything, vis-a-vis, biomass which is grown for energy purposes. So in this regard, I want to tell you, I have been associated with oil and gas industry when I went to England as a postdoctoral fellow as a research fellow in University, Loughborough University, and I was a Levering fellow. And what I did was I was doing modeling of this complex flow of gas, oil, and saline water. And I used to visualize them. So I dealt with rocks, petrochemicals, and whatnot. The petrochemistry, I mean geochemistry, and paleontology and whatnot. So it means gas, oil, and water flow, and there is a complex network inside. And so these are three-dimensional pores which are connected, and I used to make them visualizations. And in fact, I have a very beautiful paper on that in chemical engineering science. And the complexity is further increased because of sand particles, loose sand particles, like ONGC has in the Mesa field. This affects the sweep efficiency. So there is some fluid of the natural pressure, something can come out, but ultimately you have to pump something in. And that is where the drilling fluid or drilling mud. And the sweep efficiency is affected by the structure of the pore, whether this is a homogeneous network or heterogeneous, and whether it is a dolomite or a carbonate rock or some sandstone. And we used to study this sandstone structure using Beria sandstone in Pennsylvania. So you can see this stranded oil ganglia becomes the oil because of the oil continuity is broken and bypassed by the dissipating fluid. And once there is a breakthrough and you get oil and water together, where the oil and water ratio matters, then the modification of flow properties without allowing the breakthrough in the production. Well, this was my research topic, and a work, and I published one also, got patents on that. So what I'm trying to tell you, since this is related to this, what is this oil field production? The production chemistry issues in the upstream oil and gas industry occur as a result of chemical and physical changes. And this is due to the well stream fluids as they are transported from reservoir through the processing system. And in general, production problems are one of the following three. That is, one is because of fouling, and this is a very big issue in the industry. The scales are from, there are corrosion products, and there are waxes, there are asphalting, the gas hydrate, some of these issues were discussed before. And there are second type of problems which are because of the physical properties of the fluid, the foams, the emulsions, and Dr. Khandal mentioned about these micro emulsions and the visco flow, and like Dr. Jasra talked about viscophiles, and the problems that are health related, that is environmental and economic, like sulfur H2S coming out of that, and the oily water discharge and some production chemicals. And Vilas Taudeji mentioned about so much of water is coming out of, whether we can treat and recover that water, because water is going to be very expensive commodity in future. Obviously, if you look at this, the US oil field chemical market, which is shown something like $7.1 billion by 2025, and it includes all sorts of chemicals. So we must know what sort of things we can do in our green chemistry and engineering, like rheology modifiers, friction modifiers, inhibitors, demulsifiers, biocides, foamers, surfactants, and others, and whatnot. And you can see the world demand will be, last year it was something like $33 billion. So then we should ask, what is the contribution of India to this particular business? Have you done anything when there is so much of opportunity in comparison with China? And China is a good yardstick for us, because they also developed from us. In 1970, we were on the same platform. Our economy were almost the same. There was no difference. So you can imagine there is a lot of this scope. So whether they are inhibitors, demulsifiers, rheology modifiers, polymers, name it, anything of that sort, because these chemicals are required right from the primary recovery, secondary, tertiary, whether you have, the combustion flooding or water flooding, or you go to tertiary, the so-called EVO, or everywhere you require chemicals. And then ultimately you have to do the life cycle analysis. What happens to that chemical at the end of the particular process? And so we understand all these issues. And you see the market valuation of this workover and completion operation is anticipated to grow at a CAGR of 4.8% from 2017 to 2025. And because its capability to maximize the recovery of oil and gas cost effectively, and it assists in minimizing its influence on the environment, because that is very important, because we should not damage the environment. And also these products are capable and applicable in multiple operations like well completions, intervention services, fracking, EOR, and well drilling. So this is all required. So what is this green chemistry? As the name talks about, the green chemistry we can compare with brown chemistry. The invention, design, and application of chemical products and processes to reduce or to eliminate the use or generation of hazardous substances. That is green chemistry. So anything which I said before, there are about a dozen different types of chemicals which are used by oil and natural gas industry. How many of them can be produced by using green chemistry principles? And the green chemistry principles are very simple. It prevent atom economy, less hazardous synthesis, designing safer chemicals, safer solvents, design for energy efficiency, use of renewable feedstock, because if you don't have any crude oil, what do? Reduce derivatives, catalysis, whether it is chemical catalysis or biocatalysis, design for degradation, very important when you are using it in the oil field. What happens to the chemical? Can it degrade at the end of the use? The real-time analysis for pollution prevention and inherently safer chemistry for accident prevention. So, for example, in the oil field, the focus is on the biodegradable, less environmentally harmful materials. So, the little is on sustainability or the life cycle of producing these materials. And so, at an end of pipe vision is not a holistic approach. This is really only applied in certain geographic locations. Remember that. So in general, if you want to make the chemistry green, so derivatization of existing chemical type to provide a more biodegradable or less harmful structure is essential. So that means looking at some of the chemicals which are right now used can be substituted by some other chemicals. So that is possible. So we have the so-called retrosynthesis approach. So examination of other chemical structures which are known or presumed to be less harmful to the environment. For example, use of natural product type of chemistry. And of course, the corrosion inhibitors. Corrosion is because of carbon dioxide and H2S. So these production fluids contain these gases and they are corrosive, we know that. So how do you retard corrosion on the metal surface? So you have to use corrosion inhibitors or the films forming surfactants. And there are four main types. This is fatty amines and their adducts. Then quaternary ammonium salts of all varieties are used, amines and amides, imidazolines, and alkyl pyridine, alkyl quinolines, and ammonium salts are made therefrom. These are all used as corrosion inhibitors. And all of them should be made by using green chemistry. So for example, the imidazolines, the studies have shown that the optimum performance is related to the chain length. And typically with oleic acid type of chain, C18, it provides an optimum performance. So you can imagine this kind of things can be used. Or at the same time, when you have the pendant, the reaction of a pendant alkyl amine group and an imidazoline with stoichiometric amounts of acrylic acid gives the structure below, which is more water soluble because that is also required. So imagine this. Or you use a different chemistry. You have aspartic acid or alkyl polyglucosides, okay, naturally. So this is another approach. And in the case of scale inhibitors, we have polycarboxylates, some other polymers or phosphonates. So generally what is happening in this industry is chemistry is recognized as environmentally acceptable. How some authorities legislate against phosphonates regarding them as not sufficiently biodegradable because there are issues related to phosphonates. So yes, we have to look at it. And of course, all these muds, they contain this salts, so halite and sulfide, lead, zinc, etc., hexacyanoferrate salts and nitroalkylamide sand and nitrile triacetamide. So these kind of salts are used. And so de-emulsifier. So offshore oil and water separation has to happen in minutes. And these are 2 or 3 components, usually a surfactant formulated in a solvent. and many of them are not environmentally acceptable. So can we introduce biodegradability? Are they endocrine disruptors? Do they have any toxic monomers in that? So this is very, very important. In fact, we can structurally design some of these chemicals which are highly dangerous can be replaced by silicon based chemistry, okay, which is called isosteres. We can do that kind of thing, and there's ultimately the silicon becomes silica, which is naturally occurring. 27% is on Earth's crust, we know that. Are the green demulsifiers, which Dr. Khandal was also mentioning, the epoxidized fatty acid like soya, polyglycols, polyglycerols, terpene alkoxylates, alkoxylated alkyl polyglucosides. And so it is, these are old known things, but we are revisiting some of these things. And the traditional demulsifiers, because the biodegradation, many of them are alkoxylate chains, ethoxylated and procoxylated alkoxylation chains are more degradable. Polybutoxylate chains made from ring opening of butylene oxide are less biodegradable. At the same time, you know that a straight chain degrades faster than the branch chain. And so the straight polybutoxylate chains are made from ring opening of tetrahydrofuran. All these things can be certainly used. And there are many biocides used. By nature and effect, they're highly toxic, highly regulated, and there is no new innovation in this particular area. And so formaldehyde releases being examined but being considered for formaldehyde labeling. And so how do we develop this effective green biocide? So another area of research which we can look at, and again there are silicon-based substances. It's a matter of research which can be used. The other one is wax control. So inhibitors, dispersants, and all these which are polyphenylene diamine type for control of formation and deposition of petroleum waxes. The chemistries are generally polymeric and oil soluble, and obviously because of the heat, the temperature is above 60 to 70 degrees C, and the flow we can eliminate their use. So new grades are now being discovered and exploited mainly in deep water or harsh environments, and many of them have high wax content. And many of these ecosystems, such as Arctic Norway, are regarded as environmentally sensitive and require chemicals to meet stringent regulatory controls. So most chemistries are not very biodegradable and can have toxic properties. And the solvent systems which are used along with this, the inhibitors, can also have a huge issue. Therefore, this wax control has to be done by using some eco-friendly inhibitors. So the various polymers and copolymers which are used, like ethyl vinyl acetate polymers and copolymers, or acrylate polymers and copolymers, or malic anhydride copolymers, and alkyl substituted phenols as dispersants. So these are low concentration. Typically, they are in ppm. Even in the tertiary recovery, you have say polymer with some sulfur, sulfonates, or surfactants. They are always used in ppm quantities. But at the same time, they can be lost. So we have to have sustainability of these chemicals at that temperature. So the green solvents like glycols, methanol, and xylene, in the main non-polar, very few aromatic and often low solvency. Some have health effects and also problem of safety. There are esterified, alcohols or acids like good solvency, good environmental properties, and they have desirable physical properties. So they can be used. Are ester alcohols mainly in drilling applications and oleates and particularly corrosion inhibitors. So the antifoams and defoamers, main classes of product used are oil-soluble silicone defoamers, antifoams. These are very good. They are environmentally friendly. They are given a but the silicones can degrade actually, and not polyglycols. They are biodegradable. And you can imagine that they are saying the silicon material are actually, the answer is no. They can degrade to silica. And this study we have done with reference to some of the agrochemicals, particularly pesticides, and we know that we can have silicon isosteres as substituent for many of these these materials in that industry. So regulation, particularly in North Sea, has been a primary driver in greening, and North Sea was one of the major oil fields which brought in several new technologies in drilling and which we have benefited from. The regulation has primarily hazard-based and biodegradation focused, and the risk-based approaches used there in this industry. So the sustainability, this is the approach in oil and gas industry. And sustainability, may be counterintuitive, may provide an alternative greening approach, and this is what Dr. Jashra mentioned a few minutes ago. For example, the demulsifiers from polybutoxylates are environmentally acceptable when derived from tetrahydrofuran. And BASF has hard developed this THB-based bioderived, fluids, okay, demulsifiers. And even Henkel has done it. The life cycle analysis has been done. So examination of natural products for critical properties, but also ensuring they are sustainable is very important. Like the hydrate inhibitors or glycoproteins or whatever current inhibitors are there, we can substitute by another class of inhibitors. And this is where, in fact, we can go to ab initio calculations and find out which type of chemicals. In fact, many times we, the para substituted is not good, but the ortho substituted is good because it is easily degradable. So this is a new thinking in this particular chemistry. So finally, I had studied a lot of this thing as a young researcher, the interplay of surfaces, pores, interfaces, oil and gas interface, gas in water interface and gas in oil interface, in the networks and zillions of these pores. And their importance of these chemicals in this industry will continue to grow. And of course, we need better chemistry, the sustainable chemistry. And this is where the principles of green chemistry and engineering can be applied. And finally, I would say that in future, we will have, carbon-based economy only for the production of chemicals and materials and not for fuels. That is my gut feeling, and it will happen sooner than later. And as I said before, India must adopt the hydrogen economy for this particular purpose. Thank you so much for your kind attention.